Hi, welcome everyone, and welcome to my talk which is titled Going Below and Beyond Off-the-Grid Velocity Estimation from 1-bit radar Measurement. My name is Thomas Feuillen. This is a joint work with Gilles Monnoyer, Luc Vandendorpe and Laurent Jacques, and we are all from UCL in Belgium. So, for the introduction, let's say that what you want to do is to estimate the velocity of that guy, and you use a Doppler radar. First thing that you do, you transmit something, comes back to the receiving antenna. You then do the coherent demodulation, and then, in order to process those data, you need high resolution ADCs. Okay? So, now, if you look at the signal model, because we're only using a simple Doppler radar, in a sense, the coherent demodulation only measure the Doppler shift. So your baseband signal are nothing but a complex exponential whose frequencies depends on the velocity. Okay? And if you want to go even further than that and create a linear model with more than one target, the first thing that you can say is, for example, you want to recover the velocity of these two guys. First thing is you define a grid. Okay, so you have a given resolution based on your acquisition parameters. You can even go further than that and define a sparse vector where each bin is linked to a specific velocity, okay? And if you want to link this sparse vector to your measurement, you can do that using simply a Fourier transform. So what you do is you say that this element corresponds to that frequency, this element to another one, okay? And this is usually what anyone would do if you wanted to, if you had those measurements and you wanted to estimate the velocities contained in that. But with this model, there's two issues. The first one is when you have, and here we're only targeting like quite a simple application, so only looking in y dimension. But if we were to look at cases where you got lots of different sensors and you want to estimate in lots of different dimensions, so not only the velocity but the range and, for example, the angle, then you might reach a point where you have a data bottleneck. So in a sense, you have too much data that you need to sample and then transmit back to the base station for the processing. And so you might want to lower the amount of data that you need to transmit. One way of doing it is by subsampling, so taking less measurement, okay? But that might not be always optimal. Another way would be to lower the amount of, not lower the number of measurements that you need to transmit, but lower the total amount of data. And if you look at that, what it is your number of measurement times the resolution. So one way of lowering this amount of data is to lower here the resolution, okay? And this is what we're going to study here to solve this first issue. The second issue that we have is that targets do not exactly lie on the perfect grid defined by your sampling, okay? So for example here, if this is your correlation function or the result of your Fourier transform on your data, this is here the velocity that you want to estimate. And so first thing that you can do if you want to have a better accuracy might be here to increase your sampling time so that you have here a thinner main lobe, okay? But at some point, if you do Fourier transform, you will have to define some kind of grid. So where you measure, where you estimate this Fourier transform, okay? And this grid might not exactly coincide with the velocity here that you're measuring because they lie within a continuum, okay? And so, for example, in that case, this velocity is not really well represented by that point. One easy fix would be just to increase then the grid, okay? But you do that at a cost of a higher complexity in the computing. And so the question that we're asking is there a way for us to do better than that? Better than just increasing here the complexity? So what we want to do in this talk is to use 1-bit quantization, so in a sense going below typical resolution that one would use for target velocity estimation, and doing that while also looking at off-the-grid estimation, so going beyond traditional resolution, beyond traditional grid that people might use. Now we'll now look at these two fields and look how we can estimate from 1-bit measurement of the grid velocities, okay? So let's look first at the 1-bit quantization. And now the scheme that we're going to study here is the simplest 1-bit scheme that anyone can think of, which is just applying a signum operation on the real and imaginary domain. So what you're doing here is just measuring in which quadrant is the signal lying at the moment of the acquisition. Now you can ask yourself, is there's going to be cases where some information is lost. And of course, you're going to tell me, yeah, we're doing 1-bit quantization, so we lose amplitude and everything. But what I mean by that is cases where even if you have an infinite amount of measurements and the best algorithm possible, there's no way for you to recover the targets properly. And this can happen, for example, when you have two different measurements that once quantized give you exactly the same bits. And so if you get those bits, there's no way for you to tell if it was that target or that vector or the other one. And this can actually happen with Fourier transform. For example, here, what you have here is a one sparse vector, so only one target with a velocity, so a complex vector turning in the complex plane. And what you have then is a two sparse vector, so two targets, which is made of the first one plus the second one. And what you see in that case is that they always lie exactly in the same quadrant. So when you get those measurements, there's no way for you to tell if it was that vector or that one, which is a big issue, because this puts a severe bound on your reconstruction. So is there a way for us to solve this issue? We see that the main problem that we have is that even though we can get an infinite amount of measurement, we always get exactly the same bits. And so maybe one way would be for us to change the position of those thresholds randomly to get more information out of the signal. And this is called dithering. And in recent work by Laurent, Jacques, and Feuillen, they show that if this dither follows a uniform distribution that spans the same dynamic as your signal, okay, then you can hope to have better reconstruction performances. And just to give you an idea of what's happening, okay, so by doing that, and just to give you an idea of what's happening, even though it's not the whole story, is that if you look now at the expected value of your quantized and dithered data, they go back to the high resolution data. And so that's the main difference, is that before, even if you had an infinite amount of measurements, some data would be lost. One of the two targets would disappear in a sense. But now, if you want to get more out of your data, you just need to take more measurement. Okay? So just to give you a small idea of what's happening. So this is for the quantization. Let's now look at what you can do if you want to do off-the-grid estimation. As I've said, the velocities that we're looking for do not lie on the grid. They live within a continuum, okay? Which means that we need to find a way to represent those measurements efficiently, okay? So we cannot rely on that simple linear model. We need to find something that can show, that can represent properly the continuum nature of those velocities while being computationally efficient to compute, okay? So what can we do? We know that using the grid is not good enough because the resolution is not good enough. We also know that increasing the resolution, so taking more measurements, will just, in the end, increase the complexity, especially that you will need to have almost an infinite resolution. So that's no good. What else can we do? What can we do? Here, we can instead use an interpolated dictionary. So in a sense, what we're doing is we rely on the grid that we've defined, okay? And with each of these elements, we can do some kind of a Taylor expansion that allows us from this measurement to represent the velocities within that continuum, okay? And so what does it mean concretely? It means that now we have a discrete, and so this is this representation. And it means that now we have a discrete dictionary, okay? So of finite size, that allows us to represent the target within a continuum, okay? So this means that it can be also efficiently computed. So now that we've got how to represent those measurements, let's look at how to recover actually the velocities. So the first thing we're going to do is look at the continuous orthogonal matching pursuit. So looking at that algorithm using interpolated dictionaries with high resolution data, and then we'll move on to low resolution 1-bit data. So what do you do? It is an iterative algorithm that in a sense tries to estimate each target iteratively. So what you do is first you look for the element in your grid that represent best the target that you're looking for. Once you found that, you try to find the best interpolated representation of those velocities that you found up to now, okay? Once you found this representation, you then remove them from your measurement, and then you go on to look for the next velocity. Okay, so once you've done that, you also need to go from, because now up to now we are with this representation, so the interpolated dictionary, but what we want is actual velocity. So you need to translate from that interpolated dictionary to the continuous velocities. And so this is the purpose of that last step. Okay, and the point is that this algorithm has a low complexity. Okay, it can be computed quite efficiently. Now, if we look at what happens when you want to use quantized measurement, essentially what we're doing is we're now looking at the best representation using the interpolated dictionary in the quantized data. Okay, and when we want to remove the contribution of the estimated targets, we do that in the quantized space. Okay, and so the point here is that we can estimate the velocities in the continuum using quantized data, and we didn't change the complexity of the algorithm. So now let's look at some results. So what we've done is Monte-Carlo simulation, and we use different metrics to assess the quality of the developed schemes, but I'm only going to focus on one, which is the average estimation error. And so what we consider an error is just the distance between the actual velocity and what you've estimated, but normalized by the width of the main lobe. Okay, let's look now at the result for one target. So this is here the estimation error, and this is here the grid density. So when you go that way, the grid gets more and more thin, so the resolution goes up and up and up. Okay, and here we are comparing the high resolution data, the quantized data without any dithering, and the quantized data with dithering. Furthermore, we are also comparing what happens when you use simply the grid, so when you assume that the target lie on the grid even though they do not, and when you use the interpolated data. So lying on the grid is the solid line, interpolated dictionary is the dashed line. So the first thing that we see here is that if you look at the solid line, you see that all of the scheme have exactly the same accuracy. Why? Because here the problem is so simple, because you're only looking for one target, that you are only constrained not by the quality of your measurement, but by the quality of the grid. Okay, so that's why they all get exactly the same performances. If you look now at what's happening when you use the interpolated data interpolated dictionary that allows you to look beyond the grid, first thing that you see is that the high resolution data gives you the best results. Of course, it's the best quality data. But if you look then at the quantized scheme, you might see something that is a bit disappointing. Because here you see that the non-dithered one gives you a better result than the non-dithered one. So at first, it might seem a bit counterintuitive, because the whole reason of adding the dithering is for us to have better performances. But you need to remember what we're doing. Here, the problem is so simple that if you do not use any dithering, finding the rate at which the complex vector is turning is just the same as looking at the rate at which the quadrant are changing, okay, for the non-dithered scheme. But when you add the dithering, you're just actually adding noise to that. So that's why your estimate is a bit worse. But this only applies when you have one target. If you look now at what's happening when you have two targets, it tells a completely different story. Again, the high resolution data gives you the best performances, especially when you look off the grid. But now, if you look at the quantized data, you see that adding this dithering gives you a performance boost of almost 1 order of magnitude. Okay, and even more if you use the off-the-grid interpolated dictionary. Okay, and this is the main point of adding this dithering, is that now when you have more than one target, which is exactly the case that I was showing before, when for some cases, when you have, for example, two targets, one of the two targets might disappear because of the quantization. Here, adding this dithering helps you to recover everything. Okay, so now let's look at the conclusion. So what we've seen is that we combined the use of 1-bit quantization with off-the-grid estimation using a low complexity algorithm, which was quantized continuous orthogonal matching pursuit. We've also seen that if you have more than one target, you need the dithering to make it work. Otherwise, on average, you won't get the best performances. So For future work, what we've done here is quite like quite an easy setting where we're only looking in one dimension with only one sensors, but the whole scheme will make more sense if we use more than one sensor and we look for more dimensions. So as I said, the velocity, the range, and for example also the angle of arrival. Okay, so we need to look at a more complex setting, and also we want to test the resilience of the model that we've developed against some real radar measurement. So this is the end of the talk, and if you have any questions, I'd be more than happy to answer them. Thank you.